All right, section 4.4, we're dealing with a technique for solving non-homogeneous equations called undetermined coefficients. We are going to discuss this method using two different approaches. In this section, 4.4, we use what's called the superposition approach. 4.5, we'll still talk about the same method, but using a different approach called the annihilator approach. So to kind of set the stage for the kind of equations we're looking at here, we are still dealing with linear nth order DEs. Most of the ones we look at will be second order, but there's higher order than that we will look at a little bit later. And we're still assuming they have all constant coefficients, just like we did in 4.3. In fact, the only difference between the equations that we look at in this section and the ones that we looked at in 4.3 is that these are non-homogeneous. So they're not equal to 0. They're equal to some other function, g of x. Now, back in section 4.1, we developed all of that theory. And when we talked about non-homogeneous linear equations like this one, we came up with a result that said that the general solution to such an equation can be presented in the form of a complementary solution plus a particular solution. And again, remember that complementary solution is the general solution to the associated homogeneous equation to this one. So again, that's the equation that you get by throwing that g of x out and replacing it with a 0. Of course, that homogeneous case is what we looked at back in 4.3. So coming up with this guy, this complementary solution y of c, is what we were doing back in 4.3. What we need undetermined coefficients for, this method that we're going to talk about, is finding that particular solution. And once we get both of those, we put them together, and that's our general solution. So let's talk about what kind of functions g of x can be for this method to work, because it is actually a pretty restrictive method. It only works for, again, for linear differential equations with constant coefficients, and the equation has to be non-homogeneous. But not only that, the function g of x has to be one of a few different types. It doesn't work for all functions of g of x here. So to motivate this method, we notice something about particular functions that we study in calculus. There are a few functions in calculus which, when you take any number of derivatives of that function, the result is always another function that belongs to the same category of function. What I mean by that is, take polynomials as an example. Anytime you differentiate a polynomial, even if you're looking at it second, third, fourth, nth derivative, the result is always another polynomial. It never turns into anything else. The same thing is true of exponential functions, things like e to the mx, where m is some constant. Derivatives of exponential functions, no matter how many derivatives you take, you always end up with more exponential functions. Some trig functions do what we want them to do here as well. Sine and cosine in particular. If you take any number of derivatives of a sine function, the result is always either a sine or a cosine, depending on how many derivatives you took. And the same can be said of cosine as well, with some constant in front. That doesn't really happen. We don't get that nice, convenient relationship with some of the other trig functions, even though differentiating, for example, tangent of x gives you secant squared. Now what you have is a composite of a trigonometric function, secant, with a polynomial, x squared. So it gets more complicated with other trig functions, but these guys in particular fit this nice pattern with their derivatives. And that's something that we get to use in this method here. So here's the idea. Let's take a look at an actual kind of somewhat general example. Here's a second order DE, and I'm using general coefficients here, A, B, and C, but I am assuming that those are all constant coefficients. And this is equal to not 0 this time, it's non-homogeneous, so it's equal to some quadratic. In this case, x squared minus 2x plus 5. Because the function on this right-hand side, which corresponds to the g of x up here, because that's a polynomial, it kind of makes sense to guess that y, the function that we're trying to find, is also a polynomial. Because if that were the case, then y prime would be a polynomial, y double prime would also be a polynomial. Multiplying any of those polynomials by a constant would still give me a polynomial, and then adding all of those up would still give me a polynomial, which it has to be in order to equal this. So not only that, one thing that we know about polynomials is that when you take derivatives of them, the degree of that polynomial never gets bigger. It only gets smaller. So it makes sense that we don't just guess that y is any polynomial, we guess it's some quadratic, because the first and second derivatives that will show up here will never be of a degree that's higher than that. So adding all of these up would still be a quadratic. But I don't know what quadratic specifically it would be. So what we do is we set yp, remember this is your particular solution, equal to this general quadratic, ax squared plus bx plus c. Okay? Then, if you evaluate the first and second derivative of this, and then you could plug this yp prime and yp double prime all up into this equation up here. And then what we do is we basically just solve that thing for these unknown coefficients, a, b, and c. And that's where we get the name undetermined coefficients, because we don't know what a, b, and c are, but we're making an educated guess as to the form of our particular solution. Okay? So that's the idea. And again, this method will work with only specific types of functions. The ones we named up here, polynomials, exponentials, and sines and cosines in particular. But we can actually mix those functions together in a particular way and get other functions that this method will also work for. So for example, any product or sum or mix thereof of these types of functions is also usable as g of x for the method that we're going to talk about here. So functions like that, I pulled this example out of your book, it would look like this. Here's a constant function, we categorize that as a polynomial. Here's another polynomial. Here's a function that looks like a polynomial, 15x minus 6, plus an exponential function, 8e to the negative x. This, even though it's a combination of those two types, would be something that works as g of x if we wanted to apply this undetermined coefficients method. Here is a sine of 3 of x, so this is what falls under the category of sine. And 5x times cosine of 2x. It's a polynomial times a trig function. And here's another example where we're mixing up trig, sines and cosines, exponential functions, polynomials, all that stuff. Any one of these functions would be valid as a choice of g of x up here if we want to apply this method. But other functions don't work as nicely. Natural log doesn't work for this method. The reciprocal function, y over x, tangent of x, inverse sine, those functions, if we have g of x equal to any one of those, we would have to use some other method to solve that dE. Okay? So, what I'd like to do is jump right into an example. Now, again, notice what it's saying here is to solve this dE. It's a second order linear differential equation with constant coefficients, and it's also non-homogeneous because it's equal to a function of x instead of 0. We have to remember that this is a two-part deal. We need a complementary solution, and we also need a particular solution. Now, 4.3 was when we talked about finding those complementary solutions, and after having practiced that in the homework, hopefully you've found that they're actually pretty easy to do. The auxiliary equation for this would be m squared minus 1. In fact, I'm going to go like this. Aux, just for auxiliary equation, so I know what I'm looking at here. That would be equal to 0. This has solutions m equals plus or minus 1, which, remember, that means that our complementary solution is equal to c1e to the x plus c2e to the negative x. Okay? That was very quick to find that, and that's usually the case. Now we try undetermined coefficients. So, like the example, that kind of general example I looked at on the previous page, we are also dealing with a quadratic here. So I am going to make a guess as to the form of my particular solution. My guess is that yp is equal to some general quadratic, ax squared plus bx plus c. Now, in order to figure out what A, B, and C are equal to for this particular solution, I need to be able to plug this into my differential equation and attempt to solve. But that requires that I also know y double prime. So I'm going to find that, specifically yp double prime. So yp prime would be 2ax plus b. Yp double prime is going to equal just 2a. Okay? So let's put this into our differential equation and see what happens. If I put yp double prime in for y double prime here, I'm going to get 2a minus y, and here's my guess for my y. ax squared plus bx plus c, and we're setting that equal to 2x squared minus x minus 3. Okay? Now, this equation here is an identity. It's important to remember that. It's not something we solve for x, right? It's something that we want to be true for all values of x. And so that affects the way that I approach solving it. What I'm going to do is distribute the minus sign and regroup some terms so that I have something that still looks like a quadratic in standard form here. This will look like negative ax squared minus bx plus 2a minus c equals 2x squared minus x minus 3. Notice here, all I did is I took the 2a and the c, which were my constant terms, grouped them up so I know that that's the constant for the quadratic on the left-hand side, and I'm going to use that to compare to the constant on the right-hand side. In fact, I'm going to compare all the coefficients on this side with the coefficients over here. So what can I discern from this? Look at the coefficient on my x squared term, negative a. Negative a should be equal to the leading coefficient on this right-hand side if this is to be an identity. So negative a equals 2, which implies that a equals negative 2. Okay? Similarly, negative b equals negative 1. That's the coefficient on this x term, comparing that to the coefficient on this x term. That means b is just going to equal 1. Okay? What can we say about c? Well, we already know a. We said that a was equal to negative 2. So plugging that in here, 2 times negative 2 is negative 4. Negative 4 minus c equals negative 3, which implies that c equals negative 1. Okay? So now, I've basically done the bulk of the work here. The point of doing this was to find solutions for that a, b, and that c. I've now determined those coefficients, and I can put them in to my my particular solution up here. So this particular solution would be negative 2x squared plus x minus 1 after putting those in. But remember, that by itself is not the answer to the question. It's not the solution to this DE, because I'm looking for a general solution. So I have to also add my complementary solution. That means the whole shebang, the whole answer to this problem is y equals that, my complementary solution, c1 e to the x plus c2 e to the negative x, plus my particular solution that we used these coefficients to find. And remember, that's going to look like minus 2x squared plus x minus 1. That is the general solution. Now, I'm not going to do this every time, but I am going to just kind of point out that that was my complementary solution. That was my particular solution. So you're seeing where each part of that comes from. Okay? This is definitely the simplest example that we're going to do. As you're going to see with some of the examples that we do after this, the work can get extremely involved, very, very messy. And where the problems will get especially involved are the ones where this function here is a product of two different types of functions. Say, a sine function times an exponential function, or a polynomial times a cosine, or something like that. The reason why it gets so messy is because we'll show what kind of a guess we have to make for those types of functions when we get there, but finding all of those derivatives usually involves several applications of the product rule. and then simplifying every step of the way. That gets kind of tedious. So for these first couple of examples, you're going to see me write out a lot of the work. And then in future examples, I'm going to start skipping a whole lot of that algebra and even a little bit of the calculus because it's kind of just tedious work that eats up more time than I want to eat up. Okay, let's jump to this next one. This time we're looking at another second order DE, 4y double prime minus 4y prime minus 3y equals cosine of 2x. Okay, so again, as usual, we start with our auxiliary equation because we want to find a complementary solution before anything else. Okay, that's always step one. This would be our auxiliary equation. Okay, this guy factors. This one factors down to 2m minus 3 times 2m plus 1, giving me m equals negative 1/2 and 3/2 as my solutions. So this tells me that my complementary solution, yc, is equal to c1 e to the negative 1/2 x plus c2 e to the 3/2 x. Okay? As you're going to keep seeing, you know, the work that goes into finding these complementary solutions oftentimes can just fit on one line, whereas the rest of the work is going to fill up all this space here. So this time we are looking at cosine as our g of x, cosine of 2x in particular. It's tempting to want to make this assumption, yp equals a cosine of 2x. Okay, it's tempting to want to choose that. You see a cosine, so we assume our function must be a cosine. But notice, I have to plug in y prime on this left-hand side. I know that y prime of this function is going to have a sine instead of a cosine. So by plugging this function in on my left-hand side, I'm going to get a mix of both sines and cosines showing up, when really I want this thing to just come down to a cosine. So to anticipate that happening, even though I don't see a sine of 2x on that side, I include one by adding b sine of 2x into my particular solution. Okay, we have to remember to do that. So anytime we're dealing with a sine or a cosine in our g of x, the particular solution will include both of those, cosine and sine of the same argument, 2x in this case. It's a second order equation, so I need yp prime and yp double prime. This is going to be negative 2a sine of 2x plus 2b cosine of 2x. This yp double prime is going to be negative 4a cosine of 2x minus 4b sine of 2x. Okay. Now here's where things tend to get a little messy, right? So I'm actually going to write my next step down here instead of to the right. We have to take all three of these and plug them in where they would go on the left-hand side of my DE here. So starting with 4y double prime, I'm putting yp double prime into that. 4 times that. So this is negative 4a cosine of 2x minus 4b sine of 2x. Okay, that corresponds to this first term here. And then minus 4, and I plug in yp prime here, negative 2a sine of 2x plus 2b cosine of 2x. And now I plug in yp up here, minus 3 yp. So minus 3 a cosine of 2x plus b sine of 2x. And that whole thing should come out equal to cosine of 2x, right? Now, this kind of a thing, what we're seeing on the left-hand side here, is super typical of a normal undetermined coefficients problem. Once you plug in this stuff, the differential equation turns into a gigantic mess. and you'll see ones worse than this. So this is where having some sharp algebra skills, some mental algebra skills is really, really helpful, because what I want to do is group this up into really just two terms. I want to group up all my cosine of 2x terms and all of my sine of 2x terms. And it's really ideal if you can do most of the work here in your head. So I'm going to talk through what that's going to feel, or what that's going to sound like. Let's start with the cosines. I see a cosine of 2x here, here, and here. So 1, 2, 3. I want to determine what the coefficient on all of that would be once everything gets combined. So I'm going to get a negative 16a as my coefficient here. I'm going to get negative 4 times negative 4 times 2, that's negative 8. So I'm at negative 16a minus 8b. Let's ignore the minus 8b for a second, because I know I have another a over here that's going to combine with this. So negative 16a minus 3a. So that's negative 19a. Okay, and then remember we also said that we were going to have a negative 8b showing up on this side. So minus 8b cosine of 2x. Okay, you want to do that same sort of mental math combining of like terms with the sine as well. So let's see, I'm looking at my sine. A couple of them have b's as coefficients, or as a part of their coefficients. Let's start there. 4 times negative 4 again is negative 16. Negative 3 times b would be negative 3b. So negative 16b plus negative 3b is going to be minus 19b. I'll put that here because I like to have a first. Alphabetical order. Negative 4 times negative 2a would be positive 8a sine of 2x. And that whole thing should be equal to cosine of just 2x. Once again, what does that tell me? Well, compare the coefficients on my cosine and my sine here to what they would correspond to on the left-hand side. The coefficient on this cosine of 2x is a 1. So that means I can set this coefficient equal to that 1. Negative 19a minus 8b equals 1. We don't see a sine of 2x showing up on the right-hand side, so I interpret that as plus 0 sine of 2x, which means I can set this coefficient equal to 0. 8a minus 19b equals 0. And now what we have here is a system of two equations in two unknowns. These guys are really simple to solve. You can use elimination or substitution, both techniques they talk about in algebra. I am not going to go through the steps of solving this, just because that goes way back to even Algebra 1. I'm just going to give you the solutions and let you, as an exercise, fill in those gaps. But the solution to this is going to be a equals negative 8 over 425. B is going to equal negative 19 over 425. Okay? So what does that tell me about my particular solution? Well, yp then, I can plug the a and the b into here, would be negative 8 over 425 cosine of 2x minus 19 over 425 sine of 2x. Remember, that's not my solution. I need to take my complementary solution that I got here, add it to my particular solution that I got here. That is now the general solution for this dE. So that means y, my general solution, is equal to c1 e to the negative 1/2 x plus c2 e to the 3/2 x, and then plus this complementary solution, minus 8 over 425 cosine of 2x minus 19 over 425 sine of 2x. That is my general solution. Okay, so one more time, just a couple of comments, and then we're going to wrap this video up. The process that we've used to this undetermined coefficients process using the superposition approach is to take the non-homogeneous dE that we're dealing with, look at that g of x, and use it to make a guess as to our particular solution. In fact, sorry, let me back up a step. Before that, we find the complementary solution using what we did in 4.3. But then after guessing the form of this solution, we find the necessary derivatives, plug those all into your DE, and then once you do that, you tend to have an algebraic nightmare, but it's usually, doable, just kind of tedious. You can then use that to solve for all of those unknown coefficients that were originally showing up here. Once you've done that, you can put those into your particular solution, and then take that guy, add it to that guy, and you have your final answer, okay? So again, like I said before, these two examples, I took the time to kind of go through showing all of how I found all of the derivatives, how I did the mental, algebra to combine all of this junk into this. I'm going to be taking some of those steps out in the future examples because it's just time consuming, and hopefully you can fill in those gaps. But that's going to be it for this first video.